respected Dr. B.B. Kamble sir, our guest speaker from German is our young and very dynamic and very renowned author also, and Dr. Bhaskar Kamble. We are very happy to have you in Gujarat, in Guj Coast, on this auspicious day of National Mathematics Day, the birth anniversary of our legendary mathematician, and on whom we are also celebrating the birth centenary also across the all this year also. And we are happy to have this session, particularly on this National Mathematics Day, by our young mathematicians who has made his own achievement or own recognition of the not only at the national at international level, and taking our ancient mathematics, Hindu mathematics in a different height. I think most of our community science center coordinators, our science volunteers and science teachers, students, they will be very happy to interact with our guest faculty, Dr. Bhaskar Kamble, who had his career and his research at IIT, one of the premier institute of this country, IIT Kanpur, and also did a very pioneering work during his stay at Berlin, German, and now he is also quite active in his research as well as his very fundamental books on mathematics, Hindu mathematics. I am very happy to inform all our science communicators here that Dr. Bhaskar has just written quite some month before the title of the book that is Hindu mathematics, but they didn't teach you at school and why, and which is available at Amazon platform, and which is also, I think it has crossed some 7 lakhs of books and made it a recognition and record that bestseller of that book. Mathematics, how much fear, how much likeness most of the people, most of the students, most of our members that have. Having this mathematics is such a hardcore subject and very dry subject, and somebody at this young age, he has understand the concept, the philosophy, the art, and all these things, tidbits of that our ancient mathematics, and he has written a book which was a best bookseller recognition all across the globe. And I am happy while we are discussing about this program with Bhaskar. He was mentioning that he is also at the final stage of publishing the second book, which you will, I think, in the next January or February, which he will be speaking, and I think in his talk here. So with this background and with this context, we are very happy to welcome Dr. Bhaskar Kamble to our this National Mathematics Day lecture celebration at Gujarat, at Guj Coast, which is being observed at all our community science center in 33 districts with a large number of students, teachers, and the common people, those who have interest in this subject as well as the theme. In fact, we are going through this COVID-19 pandemic situation. Otherwise, it would be a very attractive and a very participatory physical meeting with a large number of students, teachers, with lots of decoration, that type of things. All our either community science center or in Guj Coast office or in our science city platform or any other places in the state. But still, the pandemic has not lessened any of the interest or any of the excitement. We are able to have all these programs and activities in our technical platforms like Google Meet or something like that, universal platform. And that technology also integrated Dr. Bhaskar from German to Gujarat, so that we are having him as our guest faculty, and we are fortunate to have it a live talk in this auspicious day and with a very interesting topic titled as at History of Hindu Mathematics from Ancient to Medieval Times. It's a very philosophical, very well researched, and very authentic, you can say, type of a message he will be communicating with us to next 45 minutes, which will be very inspiring, and I think I may be eye opener for all of us. So I request all our CSE coordinators, community, our science communicators to very carefully and attend this session and note that things, and we will be very happy to have any type of communications or this clarification or interaction with Dr. Bhaskar, who will guide us. In fact, I have also given an open invitation for our regional science museum Bhuj, where we are going to establish this very dedicated gallery on field medals. That's a very unique gallery type, like our this one Nobel Prize gallery. So with this word, I once again, on behalf of Gujarat Council on Science and Technology, Department of Science and Technology, Government of Gujarat, we welcome Dr. Bhaskar Kamble for his kind and acceptance of our invitation and delivering his very thoughtful talk on this auspicious National Mathematics Day. I hope your lecture will be very inspiring and motivating for everybody, particularly the young students and teachers who will be carry forward this message for their career and future. Thank you so much. We look forward to your very enlightening session, as well as a very continued participation and cooperation. Thank you. Thank you.
Thank you very much, sir, for your inspiring word and giving insights about the National Mathematics Day. Now I'm going to introduce our speaker. He's Dr. Bhaskar Kamble, sir. He did his MSc and PhD in theoretical physics from Indian Institute of Technology, Kanpur, and he has worked in postdoctoral research in Germany and South Korea for almost 5 years. And he is now working as a data scientist in Berlin and creating the machine learning algorithms for increasing the energy efficiency and building. And as the sir told that he is also writing one of the very interesting books named The Hindu Mathematics, and the book will be launched very soon, somewhere in the February, and the sir will be giving a few of the instead of the books while giving his sessions. So now, thank you very much, Bhaskar sir, for accepting our request and sharing your valuable time with us. Now, I would like to request you, sir, to present the contributions of the Indian mathematics starting from the 500 BC.
Okay, so thank you very much, Sahuji and Jatinji, for your kind words and your kind introduction and this invitation to for this opportunity for giving this talk on a subject which is very close to my heart. I just want to mention that I have written just one book, and this book is not available on Amazon, but it has been accepted for publication by Garuda Publications, and it's going to be published by Garuda in January or February of 2021. So just this one small point I wanted to clarify. So yeah, I will mention about my book shortly at the end of the presentation. So I would now like to start off with my presentation. So what you are seeing here is the title slide. So I just want to give a small description of some of the pictures you see here on the title slide. So the one you see on the left is the so-called Meru Prastara, and this comes from the field of prosody and linguistics, and which is actually known today as the Pascal's triangle. So it is attributed to Pascal, but it was discovered in Indian mathematics by Hemachandra, by Virahanka, and hundreds of years, several centuries before Pascal discovered them. And this second picture is the famous numbers which you see, Fibonacci numbers. And these so-called Fibonacci numbers, they actually come from the Meru Prastara, and they were given also by Hemachandra and Virahanka, and 100 years before Fibonacci. So, but still they are known as Fibonacci numbers. And finally, here, this thing is a so-called Vedic altar, which was given in the Sulba Sutras in the Vedas, and which contains the so-called Pythagoras theorem. So these are just some of the things I want to make clear about why I chose some of the pictures for this, and to set the tone for the rest of the presentation. Right. So this being the anniversary of Srinivasa Ramanujan, it is without a doubt the fact that he was one of the greatest geniuses in human history, in the history of mathematics, and his brilliance is so great that that we tend to forget the mathematical legacy that lies behind him, and we tend to ignore the rest of the mathematical legacy that came before him. So this also goes hand in hand with the belief that most of modern mathematics originated in the West, first in Greece and later in the rest of Europe during the Renaissance. And India and Hindu society have not contributed much to the development of mathematics. And so, as a corollary, Ramanujan is therefore believed to be following a tradition that is basically Western in origin and has got nothing to do with the Indian tradition. So these are some of the points which I find problematic. So which made me, embark on the study of Indian history of mathematics and ultimately to write the book. The truth is that most of the foundations of modern mathematics come from the mathematics of the Hindu civilization, and many ideas of Hindu mathematics form the core of modern mathematics. And unfortunately, in spite of this, many Hindu innovations in mathematics are attributed to Europeans, Arabs, or they are not attributed at all. So you saw in the title slide the example of Pascal's triangle, the example of the Fibonacci numbers, these being just some examples of them. And unfortunately, after more than 70 years of independence, Indians are unfortunately still not aware of this legacy. So there are some probable causes. I probably think that one of the reasons is that Indians have this general tendency to approve of something Indian only after the West approves of it. So in Ramanujan's case, it was G.H. Hardy mentored him, and then after that he became famous. So other examples like yoga and meditation, they become more and more popular in India only after it has been approved by Western medicine. So this has of course many unfortunate consequences. So one of the biggest is that we engage with our own culture only on terms decided by the West, and this I find is a very problematic thing, and this makes me want to change the situation. So this is the kind of the driving force behind this presentation that I want to give. So first of all, let's be clear about the terminology that we use. Hindu mathematics or Indian mathematics. There are various terms: Hindu mathematics, Indian mathematics, Vedic mathematics. Which one should we use? I choose the term Hindu mathematics because of the following reasons. Indian mathematics, I find it problematic because India is a political entity which was bought in 1947 with very well-defined boundaries, and it excludes what were actually part of the Hindu civilization. That is, for example, areas like Pakistan and Afghanistan in the west, and places like Bangladesh and Southeast Asia in the east. And the Hindu civilization spread across such a vast geographical area, and many of the things of Hindu mathematics arose also in these areas. For example, Takshashila was a major Hindu university in what is today Pakistan. There was this Bakshali manuscript which was discovered also in what is modern day Pakistan. Then there were several astronomical tables which were analyzed by John Playfair, which come from Thailand and so on. So for example, here in this picture you see the temple of Angkor Wat, which is in Cambodia. So, and the other reason for using the word Hindu is that Hindu is a geographical word which was used by the Persian and Arabic invaders when they invaded India. And they used this in the sense of the river, the land which is across this river. And so it's a geographical word, and it has got nothing to do with the religion as such. So in this sense, it includes also the Buddhist and Jain traditions, which is a very important point, because there have been very many important Jain mathematicians also, like Virahanka or Hemachandra or Mahavira, which that have existed in the in this civilization, and so their mathematics is also extremely important. It's an inclusive word that includes everything. So this is the reason I prefer to use the word Hindu mathematics in my talk. Okay, so here in this slide and the next slide, I want to give a very short overview of some of the major mathematicians and scholars that have existed in the Hindu civilization. So Apastamba, Manava, and Baudhayana, they were the authors of the Sulba Sutras. I showed a picture of the Sulba Sutra Vedic altar in the cover slide. So you have the so-called geometry Pythagoras theorem in their slides. So they existed much before 800 BCE at least. Then you have Panini, the author of the Ashtadhyayi. He was a very famous linguist. Pingala, also a linguist and a prosodist. And then you have Aryabhatta, who has written the Aryabhatiya and very important astronomer, mathematician. And Bhaskaravan, He lived in the 7th century CE, and he was the author of Mahabhaskarya and the Laghu Bhaskarya and the Aryabhatiya Bhashya, which is a commentary on the Aryabhatiya. Varahamihra was a very diverse mathematician who worked in almost all the areas. Brahmagupta is one of the most talented mathematicians. He lived in the 6th, 7th centuries, and his main works were the Khanda Khadyaka and the Brahmasputa Siddhanta. And Veerasena was a Jain mathematician who discovered the infinite geometric series, which we learn as geometric progressions and geometric series in school. Vateshwara was from the 9th century a very important astronomer, mathematician, and he did a lot of interesting work in interpolation of the sine function and creating sine tables and everything. Mahavira was a Jain mathematician. His work was Ganita Sara Sangraha in 9th century. It was a very important work. He discussed permutations and combinations and a lot of very recreational things in his work. And then you have Hemachandra Virahanka. I have already referred to. They were the ones who created the so-called Fibonacci sequence 100 years before Fibonacci was even born. Then Bhaskara too is one of the biggest mathematicians ever in the history of mathematics, and he was the author of the Siddhanta Shiromani, which consists of Lilavati, Bijaganita, Grahaganita, and Goladhyaya. Then Narayana Pandita, was the author of the Ganita Kaumudi. And then you have, in the end, from the 14th century onwards, you have the Kerala mathematicians, starting from Madhava, and then Parameshwara, Nilakantha, Jeshtadeva, and all that. And they were the creators of what is known today as calculus. So I will talk about these things also at the end of my presentation. Okay, so I want to start off this presentation with the so-called Pythagoras theorem, because this is one of the most important theorems in mathematics. It has applications everywhere: mathematics, science, engineering, medicine, geography, navigation, everywhere. So we know this theorem very well because it is taught in school at a young age as the following: that in a right angle triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. So since it is taught in school as a Pythagoras theorem, everyone believes it was discovered by Pythagoras. He lived in the 5th, 6th centuries BCE, so about 800 years 2,500 years from today. And then, so everyone believes that it was discovered by Pythagoras. But the truth is that it is, as I mentioned already, this is given in the Sulba Sutras that are part of the Vedas, which are earlier than 800 BCE. And there is, in fact, strong evidence that Pythagoras obtained it from the Brahmins in India. So the Brahmins were, of course, experts in the Vedas. The Vedas contain this Sulba Sutras, which in turn contains the Pythagoras theorem. So we will look at this in detail. So, but first of all, what are the Sulba Sutras? So the Sulba Sutras were written by Apastamba, Manava, and Baudhayana. So we have the Apastamba Sulba Sutras, Manava Sulba Sutra, and the Baudhayana Sulba Sutras. And they are basically instructions for constructing Vedic altars for Vedic yajnas and homas. And Sulba means a rope or a string. So a rope or a string was used to carry out measurements to measure the dimensions of the altar and everything. So that's why they are called Sulba Sutras, sutras on the Sulbas. So, and there were different constructions for constructing Vedic altars. So you want to have a square altar and a circular altar, but they both should have the same area. Or you should have, two square altars, but one should have double the area as the other one. Or you should have an altar which is the sum of the areas of two other altars, and so on and so forth. So a lot of geometrical knowledge was needed in this. And so the geometrical knowledge is then contained in these Sulba Sutras. So what is the evidence that Pythagoras obtained it from India, from the Brahmins in India, from the Vedas and everything? So well, it is recorded in history that Pythagoras is known to have traveled to India in search of knowledge and wisdom. So there are many sources, Greek sources also, who mention this. And then the very important point is that the philosophy of Pythagoras is very similar to the Hindu philosophy of birth and death, of karma, of if you do good deeds, your karma will determine your future lives, and so on. This sort of things. He believed in reincarnation. He also remembered his past lives, what he did in his past lives. So So he remembered all this, and he was also a vegetarian, which comes from the Hindu Buddhist traditions of non-violence. And yeah, he established a school of philosophy in Pythagoras, which is very similar to the Guru Shishya Parampara in the Indian civilization. So so basically, like when you consider all this, it makes it very likely that he got his philosophy, both his philosophy and the mathematics, from India, because when you consider that the Brahmins were the experts in the Vedas contain the philosophy which he talked about, and the Vedas also contain the mathematics that he spoke about. So that makes it then very clear. And all this information is very nicely collected in a German article by an Indologist called Leopold von Schroeder. He wrote an article in 1884 called Pythagoras und die Inder, in German. He wrote this in 1884. This is a picture of Leopold von Schroeder. And there, I mean, it's a very long article, and unfortunately there is no English translation available, but I have translated certain parts of it, and which I have given here. So on the right, you see the original German text, and on the left, I will just read out some of the sentences. So he writes that not only was the Pythagorean theorem known in the old priestly geometry of the Indians, but it also played the main role in their calculations, and with whose help they carried out constructions. Then he says Pythagoras was in a position to bring to Greece precisely this very theorem. And then he says in the end that it is unjust that Pythagoras should become famous for a theorem which he acquired from the Brahmins. So this is like, it's a very nice article, and yeah, it should be translated in English. I have translated parts of it, but maybe, yeah, it's a long article, but it's a very interesting article, and it connects many of the diverse pieces of evidences together. Okay, so okay, so this Pythagoras theorem is, of course, one of the most important theorems of mathematics. But the thing for which Indian mathematics is most famous is, of course, zero and the number system, the decimal number system, which we use today. And it is a very, you can imagine what a big invention this is, because ever since its invention, it has been used in the same form in which it was discovered, in which it was invented. So, so many changes have taken place in the world. There is space travel, there are computers, transistors, there's artificial intelligence, machine learning, and all these kind of things that have taken place. But the number system we are using remains the same throughout the centuries. It has not changed. So you can imagine what a big invention that has been. So what is special about it is that there is a symbol for zero. So this is a very abstract concept. How can you have a symbol for something that does not exist? Zero. That requires a big leap of imagination. And this was one thing. And the way it was used is that zero is not only a number, but it also functions as a placeholder. So for example, if you have 5 or 50, if the number 5, you have the number 5. But if you add a zero after that, suddenly it changes its value. So this is a very innovative way of representing numbers. And today it is known as the Arabic number system, and this is actually like it is falsely called the Arabic number system. Actually, it should, because it did not originate in Arabia, and even the Arabs and the Persians, they called this Indian mathematics and these numbers as Hindsat, the Indian art. And I have seen in my interactions with many people in Germany, if I happen to talk about, for example, numbers, they immediately think that the Arabic numbers, they come from Arabia, they originate in Arabia. So unfortunately, even this knowledge is not so very well known, at least outside of India, that the numbers actually come from India, from the Hindu civilization. So one of the things about this number system is that you can express an arbitrarily large numbers with only a finite number of symbols. There is a very, it's a very systematic procedure for expressing numbers. And whereas in the Roman number system, for example, you would have to keep inventing newer and newer symbols if you want to express larger and larger numbers. Okay, right. So one of the importance of numbers is that it lets you carry out operations like addition, subtraction. That is the practical use of numbers. How much is this number plus this number? How much is this number minus this number? And division, multiplication, etc. So when you do that, you will obviously run into certain problems if you restrict yourself only with positive numbers. So, for example, if you subtract 5 minus 3, if you do, it is fine. But what if you do 3 minus 5? You get a negative number. So this idea of negative numbers is also a very abstract one, and which was pioneered in the Hindu civilization. It comes from India. It comes from the Hindu civilization. The concept of negative numbers, and all these rules like positive plus positive is equal to positive, then positive minus negative is positive, then or negative times negative is positive, or positive times negative is negative, etc. All these rules were actually stated explicitly by Brahmagupta in his Brahma Sutra Siddhanta from his 7th century text. I think 628 he wrote this in his text Brahma Sutra Siddhanta. So he called, in this book, he called the negative numbers as debt, or rina in Sanskrit, rina, and positive numbers as wealth, or dhana. So it's like, the analogy becomes clear between negative and positive numbers. And you can understand that, even these negative numbers require such a leap of imagination and creativity and innovation that when the Arabs took the mathematics of Brahmagupta, they totally avoided the use of negative numbers because they just could not make sense of them. So this is some of the things. Now, yes, all right. So you can carry out operations, but the thing is, for carrying out operations, you really it's easy to carry out simple operations like addition, subtraction when you are dealing with small numbers. If you want to add 5 plus 3, for example, you can just bring 5 stones, 3 stones, bring them together, and you just get, okay, you see by looking at them, it is 8 stones. But what do you do if you have to add large numbers or multiply large numbers, divide large numbers, take square roots or cube roots? So these are all very, very interesting points. And the Hindu mathematicians, they invested a lot of time and they created many techniques for carrying out these operations of addition, subtraction, multiplication, division, taking square roots and cube roots. And we all find it very trivial, very elementary. Not because they are easy, but because we just memorize them at school when we are very, very young and when we are children, because we have to do them. Otherwise, parents may scold you, teachers may scold you, so you have to do them. And when you grow up, we just tend to forget, okay, that we had to put in so much work for understanding them. And many people also don't understand them. It is just sort of, from the memory they carry it on. And you can imagine that these methods are not trivial when you consider that in Europe till the 15th century people were using the abacus and they were not using the Indian numbers, even though they had introduced in the 12th century or so. So I would just like to summarize these 3 aspects of the number system is that it enables one to represent large numbers. Then the Brahmagupta gave the rules for dealing with 0, positive and negative numbers, and in fact these rules should be really written in gold and preserved. They are so important in the history of mathematics. And finally, you have systematic methods for carrying out arithmetic operations for quickly and in a systematic way. So I just want to here spend a few words on this interesting picture you see here on the right. So it is from a book published in 1503 by a German called Gregorius Reich. He published that in Freiburg, city in Germany, a book called Margarita Philosophica. So here you see 3 people. So here you see one man here on the left, and you can see on the table he is working with these Hindu numbers. You see the numbers 1, 2, 3, 0, etc. On the right, you see a man who is working with the abacus. So they are both counting, basically. He's using the abacus and he's using the Indian numbers. And there is this lady in the center. She signifies the lady of arithmetic. And she's looking at him and proclaiming him to be the winner. So basically, it means that, Europe was beginning to realize that the Indian numbers are superior to the earlier systems, by the end of the 14th century or so. So, okay. So how did they come to be called as Arabic numbers? Well, okay, so we know that the Islamic invasions, they started in India from about the 8th century with the invasion of Sindh by Muhammad bin Qasim. And so when the Islamic invasions began, embassies were sent from India to Baghdad. And these embassies often contained Sanskrit scholars and mathematicians and astronomers. And they took with them various Sanskrit texts on mathematics, astronomy, and even other texts like the Panchatantra also they found their way to Arabia. And because of this, the Arab world came to know about the Indian mathematics, the Hindu mathematics tradition. And this is known there as the Hind-Sat, or the Indian art of mathematics. Hindu mathematics came to be known as the Hind-Sat over there. And based on these and these were then translated into Arabic and Persian, the works of Brahmagupta, the works of Aryabhata. And based on these translations, the Persian mathematician Al-Khwarizmi, he wrote his book in 820, Kitab al-Jamwal Tafriq bi Hisab al-Hind. So which basically translates to the book of addition and subtraction on the methods after the method of the Hindus. So he explicitly calls it as the Hindu numbers. So he's not at all hiding this, that is the Hindu numbers. And later on, this book was translated into Latin and reached Europe under the name of Liber Algorithmi de Numero Indorum. So Liber means book, Algorithmi refers to Al-Khwarizmi, and so it means the book of Al-Khwarizmi on Indian numbers. So even this Latin name contains the word Indian numbers. So, okay, so the transmission from, I'll speak here in a little bit more detail about the transmission from Arabia to Europe, about the transmission of Indian mathematics from Arabia to Europe. So from the 10th century onwards, there were many prominent translators in Europe centered around Spain. For example, Gerardo of Cremona, Robert of Chester, Adelard of Bath, John of Seville, etc. And many of them, they were centered in Spain because Spain was the meeting point of the Christian, European and the Islamic cultures at that time. And Al-Khwarizmi's book, as I mentioned, is translated into Latin as Liber Algorithmi de Numero Indorum. So these translators, they translated these books from Persian and Arabic into Latin, and they reached Europe. So this was one way. The second way, the second channel, was the very influential book by Fibonacci, who was also known as Leonardo of Pisa. His book called Liber Abbasi, which he published in 1202, was also very influential in popularizing the Hindu number system in Europe. And he explicitly refers to the numbers as Indian numbers in his book. So this is how the transmission took place of arithmetic. And later on, I will also show that it applies equally well to algebra and to trigonometry and all that. Okay. So talking of algebra, so the next slide, this slide, shows you it shows you an excerpt from one of Bhaskara's works on Bijaganita, in fact on algebra. So Bijaganita is in fact the Hindu name for algebra. So what we know today as algebra was called as Bijaganita in the Hindu mathematical tradition. It was also known as Avyakta Ganita, and the reasons for this are very important, are very interesting. Why it is called Bijaganita, why it's called Avyakta Ganita. I explore these reasons in great detail in my book, how they are connected with the Indian philosophical systems and everything. But here I will just stick to the main points here. So what is algebra? In school, we learn algebra as basically, you have an unknown and you want to find the unknown. So you set up an algebraic equation, you solve the equation and you find an unknown. So a typical problem could be, for example, which I have mentioned here, a person has 300 rupees and 6 horses. Another person has 10 horses and 100 rupees debt. The property of the two is equal and the price of the horses is the same. What is the value of each person's property? So we know this in school, how do we do this? We can say that, okay, let the price of the horse be X, okay? And then the first person has 6 horses. So 6X is the value of the horse and he has plus 300 rupees. So 6X plus 300 is his property. The second person has 10 horses. So the property of the horse is 10 times X, but he has 100 rupees debt. So 10X minus 100. So the two being equal, you say 6X plus 300 is equal to 10X minus 100. Solve this, you get X equal to 100. And finally, that means that 6X plus 300 is 900. So each person has 900 rupees. So that's the property. So this is one way of, one use of algebra. The other use of algebra is that you can use symbols to state general results. So for example, in a right angle triangle, you have a square plus b square equal to c square. That means you don't need to, list out all the possible right angle triangles. Just this one single formula contains all the right angle triangles that are ever possible, that can ever exist. This one single formula contains everything. So these are the very powerful uses of algebra. And what is what not known is that this method was developed in the Indian civilization, Hindu civilization, and known as Bijaganita. And today we use symbols like X, Y, Z or alpha, beta, gamma for the symbols. And what was used in the Indian Hindu civilization was different words from Sanskrit. So one of the what we call x, you can was used basically the corresponding analogy for this was the so-called yavat tavat, which comes from Sanskrit, which means as much as, literally means as much as, yavat tavat, and this was shortened as ya in the Sanskrit texts. So it's the counterpart of x today, what we call as x was the ya. And there were also other symbols used, the letters of the alphabet, k, k, g, g, or the color names were used. So for the symbols. And if you want to express something like x square, this was expressed as ya v. So that means ya stands for yavat tavat and v stands for varga, and varga means square in Sanskrit. So ya v becomes x square. And it's very interesting that the Italian algebraist Raphael Bombelli in the 16th century, he also used the word tanto for denoting an unknown. And in Italian, tanto also means as much as, just like yavat tavat means the same in Sanskrit, as much as. So here on this left you see a picture, and this picture is a snapshot from Bhaskara's Bijaganita, and you see here exactly this problem which I had described in the previous slide with the horses. So ya stands for x here and 6, so 6x, and ru stands for basically plus and 300, so 6x plus 300, and then you have here ya 10, so 10x, ru 100 dot, so dot stands for minus, so 10x minus 100. So actually the example that I showed you some time back was actually from Bhaskara's Bijaganita, and from the example comes from his Bijaganita and this with the horses. So yeah, this is one thing, of course, and what I have not touched upon, but it's also important to mention, is that more advanced concepts such as equations with several variables, simultaneous equations, quadratic equations, they were all addressed in the Hindu algebra texts. Then also quite advanced concepts like the so-called Pell's equation, which is basically indeterminate equation with integral solutions. And for solving this, advanced methods such as Kuttaka and the Chakravala methods were developed by the Hindu mathematicians Jayadeva, Bhaskara, Brahmagupta. And these methods were discovered in Europe only in the around the 18th century by people like Fermat and others. So, okay. So transmission of algebra was, of course, just like arithmetic. First, it went to Arabia and then it went to Europe. And it is, believed by many people that Al-Khwarizmi is the inventor of algebra, but it is absolutely not true, because as we have seen, his works were based on the works of Brahmagupta and Aryabhatta and other astronomy, other mathematical works. And so it is basically like, the Indian algebra travels to Arabia and then it travels to Europe. So there is, a lot of proof for this. I will just give a small proof from one of Raphael Bombelli's books. This was again from the 16th century. This Bombelli wrote this book, Algebra. So this is in Italian. So and the text which is marked here in red, I have translated here into English. And then you basically see here that. So he claims, so he says here explicitly that I have been made aware that this discipline of algebra belongs to the Indians before the Arabs. So this was all well known in those times, that it all comes from India. It is only in recent years that this whole narrative is being started, that okay, algebra comes from Al-Khwarizmi and all that. So it is like, yeah, it's all known. It's all nothing new as such. Okay, so after algebra, I want to come to the topic of trigonometry. My aim in giving this presentation is showing just a few key areas of mathematics which play a key role in today's world, and which actually come from India, but which is not attributed as such. So, and trigonometry definitely falls into this category, because trigonometry is such an important branch of science. It has of mathematics. It has applications everywhere: physics, chemistry, all branches of engineering, astronomy, also navigation, medicine, everywhere. So it is one of the most important branches of mathematics for sure. And it is in school. It is usually introduced under the topic of heights and distances. So you have the right angle triangle, opposite side, adjacent side, hypotenuse, and the sine is described as opposite by hypotenuse, etc. And then at a later stage, one understands trigonometry in terms of the circle. So you have a circle and any angle theta, for example, the sine of that angle theta will be the y coordinate of the point on the circumference, and the cosine will be the x coordinate of the point on the circumference. And you have also ideas like the sine and the cosine for any angle between 0 and 360 degrees. So this modern conception of the sine and cosine in terms of the circle and all this idea, this modern conception of trigonometry, it all comes from Hindu mathematics. So this, for example, Aryabhatta gives a value of 24 sine tables in the first quadrant, and there he uses the notion of the half chord. We will come to that in the next slide. He uses and this is exactly similar to the notion of the modern sine function, and even the names sine and cosine are of Hindu origin. And how is that? Let us look at this in some detail. So, for example, you have here the circle I show here on the right. In this circle, you have the angle theta, and I show here in red the arc ABC. The arc ABC is, it looks like a bow, and ADC looks like a string. So ABC was known in Hindu mathematics as dhanu or chapa, because dhanush means a bow in Sanskrit, and chapa also means a bow. And the line AC was called jya or jiva. And AC, the jya or jiva means string in Sanskrit, and it looks like the string of the bow. And AD was called the ardha jya because it is half of AC. So ardha means half, so half of AC. And if you just look at it a little more carefully, you can easily see that AD is equal to the radius of the circle times sine theta. So ardha jya was actually r times sine theta, and in time to shorten it, ardha jya became shortened as jya itself. So AD was the jya, and which is equal to r times sine theta. And OD was called the cotigya. So OD is equal to r of cosine theta, and that becomes cotigya. And so this jya and cotigya, they were the modern day sine and cosine functions. Now what happened is that the Sanskrit mathematical texts were translated into Arabic and Persian, and in Arabic the word jya was translated as jaib. And in Arabic, this word jaib means bay or gulf in Arabic. And then when these words were translated from Arabic into Latin by the European translators, they substituted the Latin word for bay or gulf. And the Latin word for bay or gulf is sinus. And that's how the word sinus has stuck today, which originally comes from the jya of Hindu mathematics. And the cotigya likewise became cosinus, which is the cosine of today. So that is the history behind sine and cosine. So in trigonometry, there are also other important concepts. The angle of the value of sine and cosine between 0 and 360 degrees, whether they are positive or negative in the different quadrants, and these are all addressed in the works of the Hindu mathematicians like Manjula, Bhaskara, and everything. I will not go into them in detail because of time, but yeah. So and then you have Aryabhatta's value of pi, and there were interesting interpolation methods for finding sine values and all that. And you can have a look at C.K. Raju's book, Cultural Foundations of Mathematics. It gives a great account of all this. So I just give a small example of all these things. One is this equation that we learn in school, that is sine of a plus b is sine a cosine b plus cosine a times sine b. And similarly for sine of a minus b, and analogous equations for cosine. So this is a verse from Bhaskara's Siddhanta Shiromani section Goladhyaya. So he gives here the verse, the Sanskrit verse, which gives you this formula for sine of a plus b and sine of a minus b. So the r sines of any two arcs of a circle are reciprocally multiplied by r cosines. So just forget about the r, because today we don't speak about r, but it basically means you reciprocally multiply sine a cos b and cos a sine b. Then the products are divided by the radius. We don't need to do that because we don't worry about the radius in today's definition. So we just take this product and this product. Then you take the sum of the quotients. In this case, there is no quotient. So you just take the sum of this, and the sum of this is equal to the r sine of the sum of the two arcs. So it is basically equal to the sine of the two angles, because they speak of arcs, but we speak of angles today. So this means that sine a cosine b plus cosine a sine b is equal to sine of a plus b. And he says also the analogously that when you do sine of a minus b, you get sine a cos b minus cosine a sine b. So, and you get the same formula when you apply the same formula for using the fact that cosine theta is sine of 90 minus theta, you get the results for cosine a plus b and cosine a minus b. So these are, this is just one example I want to state from here. Okay, so the interesting thing is that in many of these ideas of Bhaskara, Aryabhatta, Brahmagupta, they had these ideas like interpolation and finding out the sine tables and astronomical concepts like for the velocity of a planet and everything. So all these were actually how do you say? the seeds of the calculus, so to speak, were hidden in this mathematics. Okay, so for example, and this brings me to the next topic that I want to talk about after trigonometry, that is that of calculus. So, for example, Aryabhatta in his sine table, he makes use of the discrete version of the fact that the second derivative of the sine is proportional to the sine itself. So obviously it is a lot of mathematical detail, and it would be too much technical if I would go into the details right now in this presentation, but I have discussed this in quite some detail in my book. There it is, you can read that in there. And also C.K. Raju discusses in his Cultural Foundations of Mathematics, which in a very clear way. And so this is a very, the seeds of these calculus which later were developed by the Kerala mathematicians, they are already present here in the works of Aryabhatta and Bhaskara and all that. So Bhaskara used the concept of tatkalika gati, or instantaneous velocity, which basically very basically used the fact that the derivative of the sine function is equal to the cosine. This is how we would say in modern language. Then Bhaskara also made use of the so-called Rolle's theorem, which says that a function's derivative vanishes at some point between 2 points where the function has equal values, which was enunciated by Michel Rolle in the 17th century. And Bhaskara in his Siddhanta Shiromani also gives the expression for the area and volume of a sphere. So 4 pi r square is the area and 4 by 3 pi r cube is the volume. And his method is very close to the method of integral calculus, which we learned in school, but he did not give the full proof of that. He just gave a demonstration that it is true, and then he gave the final result. And the final result was actually given by the Kerala mathematicians in the 14th century onwards. So, which is okay. So that brings us to the topic of the Kerala mathematicians. So, at this point in time, that is around the 14th century, a very interesting thing starts happening. Till about the 14th century, the development of mathematics was taking place all over India. So Gujarat, North India, Maharashtra, and Karnataka, South India, everywhere, East India, and everything. But somehow, from about this 14th century, 12th, 14th century, so Bhaskara was the maybe the last major mathematician. From this time about, the development of mathematics came to nearly to a stop in North India and the rest of India. But it continued in South India because the rest of India was attacked by the Islamic invasions, and that literally put a stop to the development of knowledge. So, for example, the famous university, Nalanda University in Bihar was destroyed, and many other universities were destroyed in India. So that brought a stop to the development of knowledge of mathematics in North India and the rest of India. But it continued in the south because of the Vijayanagara Empire, which offered a protection against the Islamic invasions. So the Vijayanagara Empire was centered at Hampi, and it was in this empire that mathematics and other sciences were able to flourish. So in the 14th century, we have the famous Madhava, who carried on the tradition of mathematics, and his school of mathematics, and his followers, like for example Neelakantha, who was the author of the Tantra Sangraha and the Aryabhatiya Bhashya, and Jeshtadeva, who was the author of the Yukti Bhasha, which was written in Malayalam, and Shankaravarman and many others. And they made many groundbreaking discoveries in astronomy, mathematics, and which actually led to the development of calculus in the modern era. So let us look at some of these their achievements. I will have to go through them very fast because it otherwise would be very much detailed. Would be too much detail for this presentation. So, for example, one of the results of the Kerala mathematicians is the Taylor series expansion for sine and cosine. So Taylor introduced them in 1715, but Madhava had given them already in the 14th century. So, you have these series expansion for sine x is equal to x minus x cubed by 3 factorial plus x5 by 5 factorial, etc. And cosine x is given by 1 minus x squared by 2 factorial plus x4 by 4 factorial, etc. So then you have some other results of the Kerala mathematicians, like the series for the inverse tangent function, which is given by x minus x cubed by 3 plus x5 by 5, etc. And this is today known as the Gregory series, after James Gregory, who published them in 1668. And the series for pi by 4, which is given by 1 minus 1/3 plus 1/5 minus 1/7, etc., which is today known as the Leibniz series, which was discovered by Leibniz in the 17th century. but already it was discovered by the Kerala mathematicians in the 14th century. So this is just some other examples of Indian mathematical achievements that are attributed to Europeans. So right. Okay, so what are the uses of all these series expansion and all these things? Well, there are very practical applications for these. The two of the most important applications in the Indian civilization were in astronomy and navigation. So, when you study astronomy, you will come across the concept of the celestial sphere. So here I have shown a picture of the celestial sphere, which is basically the Earth at the center and all the other objects move around the Earth. So it's a basically geocentric frame which is used today for describing the motion of bodies relative to the Earth. So wherever you have a sphere, you obviously have circles, and wherever you have circles, you have trigonometry, and wherever you have trigonometry, you need sine and cosine functions. So that is one of the things. Then the other application is navigation. So just like the celestial sphere, the Earth also is like a huge sphere, not exactly spherical, but to a great approximation, it's a spherical object. So also for navigation, you need to have a good amount of knowledge of astronomy and trigonometry. And again, these functions like sine and cosine come in. And because of the scale of these objects, Earth or the celestial sphere or the Earth and the heavenly objects, small uncertainties in trigonometric functions can lead to huge errors. So that's why a high level of accuracy is very important. So Madhava he wrote a table of sine functions which were highly accurate. In fact, they were accurate for 1 part in 10 million. So like up to 7 or 8 decimal places they were accurate. And with these series, it also became possible to calculate the value of pi to a very high accuracy. So this is from Shankara Varman in his Sadratnamala, he gives the value of pi up to 17 decimal places. And all this was, they used the so-called Katapayadi system of notation, which I have also described in my book, how it works. And they used the sexagesimal notation for numbers. I mean, not in the sense of like the degrees, minutes, and seconds, exactly the way we use today for describing angles. Okay, so these were some of the uses, and now to wrap up the presentation, I want to speak about the possible transmission of calculus to Europe. So I have already spoken about how arithmetic, algebra, and trigonometry went from India to the Arab world, and from the Arab world to Europe. In the case of calculus, it's a very interesting situation because in this case, the transmission actually happened directly from India to Europe, not through the Arabs. And of course, today we usually believe that calculus is the single-handed discovery by Newton and Leibniz, and they discovered calculus and all that. This history is taught to us, but as we will see, this history is not really true history. So we will look at some of the reasons why it was that. So why is it that Europe needed this knowledge of mathematics from the Indian civilization, from Kerala? There were two very important reasons. One reason was that till the 16th century, Europe was following the so-called Julian calendar. So the Julian calendar was quite inaccurate, and because of this, the Christian festival of Easter was going further and further away from the equinox, and this was very bad for the church. So they needed a good calendar for this. And as you know, calendar is dependent very much on the astronomical bodies, the motion of the sun and the stars and the planets. And for a good calendar, you need good astronomy. And for good astronomy, you need good mathematics. And secondly, Europe was also becoming more and more imperialist. That is, it wanted more and more colonies. So that means it wanted to carry out journeys to faraway lands in Africa, Asia, the Americas. And for this, they needed good navigation. And so for navigation, again, you need astronomy. So these are the two main reasons. I want to first address the issue of the calendar, the issue of the calendar. So as I said, the Julian calendar used till the 16th century was extremely inaccurate, and the church therefore needed an improved calendar. So it was already on the lookout for astronomical and calendrical knowledge from India. So in 1498, Vasco da Gama had, so to speak, discovered the sea route to India, and he had arrived in Kerala, which was the seat of the Kerala mathematics. Okay, so Europe already knew that India has a good amount of mathematical knowledge, and they also knew it, because Fibonacci had published his book where he had talked about the Indian numbers. They knew about the Arabic and Persian translations of the Sanskrit works, so they knew that India has this tradition. So they were on the lookout for this. So the church wanted a calendar, so they set up a calendar reform committee, and the head of this committee was Christoph Clavius. He was a Jesuit priest, and he was also a mathematician, and he introduced mathematics in the church curriculum. So, and in 1542, the Portuguese missionary Francis Xavier, he arrived in India, and after that, many Jesuit missionaries came to India. So Christoph Clavius, he was, as I said, he was on the lookout for this mathematical knowledge. So he trained several Jesuit missionaries, for example, Matteo Ricci, Johann Schreck, Antonio Rubino. He trained them in mathematics and astronomy, and these were sent to Kerala in the year 1578 and to acquire Indian knowledge. And it is now very surprising and very interesting that shortly afterwards, in 1582, the calendar reform was carried out in Europe based on the suggestions from Christoph Clavius himself. So there is, so it's a very interesting coincidence, if it is a coincidence at all. And the new calendar is today known as the Gregorian calendar. So this is and of course we know that the Indians possessed a very reliable calendar, and so on. Okay, so the second part is the aspect of imperialism in Europe. So because of imperialism, European countries wanted to go and carry out journeys to faraway lands. But Europe's state of navigation was very bad, and many people lost their lives in sea voyages because they just lost their way, and and many people died because of this. So, and it was so bad, in fact, that even though we are told that Vasco da Gama had discovered the sea route to India, the truth is that he was escorted from the African coast, from the East African coast, Malindi, all the way to Kerala by an Indian navigator who is believed to be a Gujarati, in fact. And so basically, even there, so much for discovering the sea route to India. And at the same time, this shows the fact that he was escorted by an Indian shows that Indians carried regular trade with other countries, in fact, both to the west and east of India. And they were famous for their skills in navigation and shipbuilding. And navigation, of course, depends on astronomy, and the Indian mathematical texts were full of methods for finding the latitude and longitude based on the positions of astronomical objects. So, for example, Bhaskara in his Laghu Bhaskariya, he describes several such methods for finding out the latitude and longitude based on the positions of the astronomical objects. And the Jesuits in Kerala were therefore in a perfect position to acquire this knowledge and transmit it to Europe. So, but of course, the church could not accept using pagan or heathen sources of knowledge, because that would be like heresy, or that would be blasphemy to use knowledge from other sources. So there was a tendency to hide this knowledge, the true sources of this knowledge. So let us look at what happens shortly after the Jesuits land in Kerala. What happens to the development of mathematics in Europe at that time? So. So it's very interesting that Galileo and his students, Torricelli and Cavalieri, shortly afterwards, they started working on the subject of infinitesimals. And in fact, in Europe, shortly after this time, there was an explosion in the study of infinitesimals. Infinitesimals are very small quantities which are not zero, but which are really arbitrarily small quantities which play a key role in the formulation of calculus. So the fact is that Galileo was a very close friend with Christoph Clavius, and they used to often have interactions with each other, and they used to discuss often with each other. And Galileo had close contact with the Collegio Romano, with the University of Coimbra. All these universities were Jesuit universities where the Jesuits would send their material from India, and he would have contact to all these sources. And so it is not at all surprising if he came across the sources of the Kerala mathematics in these sources. No? And then the Gregory series we saw some time back, which was discovered by the Kerala mathematicians. We saw that the Gregory series. He was actually a student of Galileo between 1664 and 1668. And shortly after his stay in Italy with Galileo, he came up with the Gregory series. So this is also another coincidence. Then I mentioned earlier that Nilakantha had spoken about the Madhava had given the value of the sine function for various angles to a very high degree of accuracy, 1 part in 10 million. Very interestingly, Christoph Clavius in his book Astrolabium, I have given a snapshot of his book Astrolabium. He gives also exactly the same level of accuracy for this sine function for different angles. So this, for example, is the sine of 30. So you see it is 0.5. So this is like the sine tables of Christoph Clavius, and he never mentions how he comes up with these series. What is the method he uses for describing these series? One more coincidence is that the planetary Nilakantha had proposed a planetary model, and exactly in the 15th century, and exactly this model was proposed by Tycho Brahe in the late 16th century. So this planetary model was So this is also one of those coincidences. And Leibniz, one of the co-discoverers of calculus, he was in close contact with the Jesuits stationed in India and China. There are many letters of his, where he has corresponded with them, and so it is very much probable that he got the Leibniz series for pi, from the Jesuits stationed in Kerala. And finally, Isaac Newton, the other co-discoverer of calculus, his teacher, one of his teachers was Isaac Barrow, who was tutored by Viviani, who was internal student of Galileo and Torricelli. And as we saw, Galileo and Torricelli had access to the Jesuit sources in the Collegio Romano and University of Coimbra. And another teacher of Newton was Gil de Roberval, who in turn was a student of Mersenne. And Mersenne is also known to have very close contact with Indian mathematical sources. And so all this makes it a very likely that the calculus actually, what we know as calculus today, is comes from the Kerala mathematics and from the Indian mathematics at large. Okay, so I slowly come to the end of my presentation. Why is all this important? Because you hear a common statement from many people say, okay, yeah, why is it important? We may have been great in the past, but what are we doing today? We are just doing second-hand stuff, and we are not doing anything innovative and anything. So I have a series of answers for this. My most important answer is that, well, it is important for the sake of truth alone that you should know the truth. That alone is sufficient reason that we should know all the mathematical legacy of our civilization. The second important reason, as far as I see it, is that we have been looking at everything through Western lens, right from history, science, and even our own identity. Like, for example, even in history, we are taught about this fictitious Aryan race theory, or that everything in Hindu civilization comes from caste, and which is like, which is this colonial history which was introduced by the British. We are being taught since school, and the word caste itself is a Portuguese word, and so it has So the point is that how can we be original if our own sense of history and identity comes from the West? If we have blindly imported them and we blindly parrot the history taught to us during colonial times. And it's also a matter of respecting our own legacy, because nobody else will do it for us. Because as we see, the West would be happy to continue with the narrative of the so-called Pythagoras theorem or Leibniz series or Fibonacci numbers or things like that. And finally, it is very important to become aware of our own legacy if we are to develop our original worldview, our original epistemology, and our original framework of knowledge with which we can understand and investigate and look at the world around us. So finally, here are some of the references I have used. Datta and Singh is a very encyclopedic reference, very thorough reference, huge reference. Then there is a series of video lectures from IIT Bombay. I have given the YouTube link here, online link here, and you can look at the book also, Tantra Sangraha of Nilakantha, translated by Ramath Subramaniam and Sriram, and C.K. Raju's works of Cultural Foundations of Mathematics talks about the transmission of calculus from India to Europe, and this Springer Encyclopedia. And finally, my book is to be published by Garuda Publications in February of next year. And you can follow Garuda Prakashan on Twitter for updates. And my own Twitter profile is Neeru Prastara. And with this, I come to the end of the presentation. Thank you very much for your kind attention. Okay.
Thank you very much, sir, for such informative sessions. In fact, we are so excited to know that the things we are learning in the school times have really deep rooted with our ancient literature as well. Though the word are new to us, but the things are really the same that has been taught in the schools. The Anka Ganit, the Beej Ganit, the Trigonometry are really, really wonderful to see how rich the legacy of our ancient mathematicians that have brought by today user.
Yeah. Thank you.
I think it's a wonderful presentation. It's a great compliment to Dr. Bhaskar Kamble. Thank you so much for your patience presenting here. It's a very hard talk, we understand, and you have covered the entire gamut of this ancient India from just before 3000 years or something like that, that we learned in our primary to secondary to higher secondary and to higher education also. It's a very snapshot of entire bird's view, we can say, that of ancient Indian contribution or the Hindu versions of mathematics type of things. I think it can't be discussed in just like 45 minutes or 1 hour talk. It can be around the year, lots of things there in a fragmentation way or something. But you give in a very beautiful snapshot of these things and very interesting manner. And all these slides are very nicely designed and with all lots of illustrations and these things also. It will be very eye-catching. And I think all our coordinators and communicators, they have received that same types of feelings and enlightening experience with these sessions. I think we can give some time to if any queries or any these things, feedbacks from our CSE coordinators or communicators. Jatin, you can allow any of our members, they can have some sort something to say.
Oh, sure, sir. Sure, sir. We have one question from by Rahul. Sir, you can unmute your mic and ask the questions.
Hello, sir. Am I audible?
Yes.
Sir, my question is that Srinivasa Ramanujan proved that the sum of all natural numbers is -1 upon 12. How is it possible, sir?
I'm actually not so much familiar with the works of Ramanujan, so maybe I'm not the right person. But yesterday, I think there was a talk. You could have asked it in that talk, because the person had given a talk explicitly on Ramanujan's mathematics. But I'm not sure about this, so I cannot answer this question. I think it is also not really relevant to the topic that I spoke about. So.
Yeah, sir. Sure, sure. We will put these questions to our previous speaker as well. Yes.
Mm-hmm.
Any other questions from other participants who have attended the session through the Google Meet link? Yes, Vivek, sir. Please unmute your mic and please ask the question. Vivekji, we are not able to hear you properly. Please unmute your mic and then you can ask the question. I think he's facing some network problem. Is there any questions from other participants? Vivek Sinha, you can drop questions in the chat box and then probably we can bring it up.
I think we have Dr. B.B. Kamble, sir. Would you like to speak something, sir? Requesting that we are very happy to have a talk by Dr. Bhaskar. It's a very happy moment for everybody. I think we should thank you and Madam for having this session also. And we'd like to have a quick feedback or word to you, sir.
Hello, sir. Sorry, sir, interrupt to you, but sir, I have a query. Can I ask?
Yeah, please. Yeah. So somebody just asked, how can I understand -2 times -3 is +6 on the real line? So you can just think of it as a reflection along the real line. So 1 minus 1 becomes a reflection, and -1 times -1 is +1 because it's a reflection of a reflection. So it takes you back to the positive. So this is one way of understanding this. So somebody just asked me a question here, that why is -2 times -3 equal to +6? So for that, you just need to know that why is -1 times -1 equal to +1. So my answer would be that, -1 is a reflection of 1, and -1 times -1 is again a reflection of that. So it takes you back to 1. So this is one way of understanding this. Okay, so there seem to be no other questions.
No, can I make a comment?
Yes.
Yeah, please.
Yeah, okay. Now, for these are basic arithmetic operations, like, minus is plus, or so plus minus is minus, or plus is plus, and plus minus is minus. The concept of number line becomes very useful. If you use a number line, okay, so that say at the origin is 0, on the right hand side you have positive numbers, on the left hand side you have negative numbers. Okay, then say it really works out very well, and all these concepts say could be explained and say very well say to a novice. So I think that is something I cannot be explained here, as it needs say some demonstration, or maybe say some more explanation. So
Yes.
that you can find the references to this at many places. Thank you.
Yes, yes, yes.
But it has been a very useful session. We must know our own heritage. Say what all we had in our past. What is the and what has been our heritage? I think that's we have got to know. So from that point of view, it's certainly a very good session, and enjoyed it. Thank you.
Okay. Sahuji, you are muted. Sahuji, you are muted.
Your mic is mute, sir.
Sorry. Thank you so much, sir, and thank you so much, dear Dr. Bhaskar. As I mentioned, this is the beginning, and we are very happy that you are so kind to accept our invitation and talk to our students, teachers, and communicators. And as the topic and your work is very interesting and exciting, and very thought-provoking also, to understand our own heritage and our own past, glorious past about science, mathematics. We'll be requesting more often for your convenient time and your consent. So this is a wonderful talk. I think this is the best talk that we can expect the day like in National Mathematics Day. Thank you so much, and we'll be continue to communicate, to coordinate, and to have such type of programs. We wish a very great success in your mission. So we look forward to see your book also in early 2021 January or February, as you were mentioning. And in fact, by that time we can have some good program also with your opening or your launch of that book. And we want you to bring more closely to our community, our students, so that they can take you as a real mentor or role model. Thank you so much. And once again, we'll be in touch with you, and we'll look forward for your kind feedbacks and comments. Thank you.
Thank you very much, Dr. Sahu, also for this wonderful opportunity for letting me present here. And I look forward to seeing you again.
Yeah.
Thank you very much.
Thanks.
Yeah.
Thanks. Take care.
Okay.